This tutorial will help us calculate the moment of inertia and actually define what is that for a body. Suppose we have mass m and we apply a force, and if we apply a force it will actually start moving, but it will be more difficult to move higher masses. So mass is, in this case, when we're talking about translation, mass is the inertial property, which means the more the mass, the more force you need in order to change its state of motion. When talking about rotation, well, in rotation, the inertial property, which means the more this inertial property, the more difficult is to change its state of motion, is, for instance, also depending on the mass, but also on the radius. So if we have, for instance, the axis of rotation here, the distance of each and every particle will also be important, and this is considered the moment of inertia, which is for instance the integral of the radius to the square where it is located, each particle, times the differential of mass, and we are going to add each contribution of mass. So it is important the mass, but it is important also the position of the mass, where the mass is located with respect to the axis of rotation, and that is called, or we're going to define it as a radius. Now don't worry a lot, because we have certain figures which are already provided. For instance, the moment of inertia of the slender rod, where the axis of rotation is its center of mass, is 1/12 of mass length of the rod to the square. And we can discuss each and every one of these moments of inertia, but maybe you can take a minute by yourselves to actually analyze these. So for instance, we have rectangular plates, we have also this rotating by the center of mass, but also at an axis along the edge. That could be the door, for instance. We also have cylinders and spheres, and analyze each and every one of these, and we're going to proceed to how to calculate other moments of inertia with respect to these, if they are not rotating, for instance, in the center of mass. So first things first. Now imagine that you have a bar, and according to the table, if the bar is, for instance, rotating at its center of mass, then the moment of inertia is 1/12 of mass length to the square. So for instance, this has length L, and its moment of inertia is 1/12 of mass length to the square if this is rotating at the center of mass. But not all the bars are rotating at the center of mass. It might actually happen that it is rotating, for instance, a distance of, I don't know, let's suppose 1/3 of L from the center of mass. So this is the location of the center of mass, and it's rotating 1/3 of L. So the moment of inertia is going to be given as the moment of inertia of the center of mass plus the mass times the distance that you actually moved the axis of rotation from the center of mass to the square. So in this case, this is 1/12 of mass length squared plus mass times 1/3 of length to the square. So this distance, for instance, is this distance from the center of mass to the place of the new axis of rotation. This is relevant because if you have a pendulum, it is very important to state where is the pivot. For instance, if the pivot is here, this is the axis of rotation, then you have a bar of length L, and let's suppose that it's composed as well with a sphere of radius R. Well, the moment of inertia is going to be the moment of inertia of the bar plus the moment of inertia of the sphere, since these are scalars. But nor the bar nor the sphere are rotating at the center of mass. So you have to first calculate the moment of inertia of the bar, then the moment of inertia of the sphere, and then add them up. So we discussed what is the moment of inertia and how to calculate the moment of inertia for regular forms, and how to apply the parallel access theorem, and how to add moments of inertia for a composed object.